In this video, we're going to discuss a variety of different examples making use of the pigeonhole principle. So this example says if we pick 5 different numbers that range from 1 to 8, we're going to try to show that 2 of them must add up to 9. So let's just try to pick random numbers and see what happens. Okay, so I got 1, 3, 5, 7, and 8. And in this case, 1 and 8 add up to 9. But you might say, well, you picked 1 and 8. You didn't have to pick 1 and 8. You could have, instead of picking 1, we could have picked 2. But then, 2 and 7 would add up to 9. So our job is to prove that there will always be a sum that adds up to 9, no matter what. And to do this proof, it would be pretty cumbersome to try all of the possibilities. So instead of trying all the possibilities, we're going to try to make use of the pigeonhole principle. So what kind of pairing do we want to occur? We want 2 numbers to get paired together so that they add up to 9. So our pigeons can be these 5 different numbers, and our holes can be all of the ways to add 2 of these integers up to 9. So we have 4 total pairs. So when these pigeons on the left fly into the corresponding holes on the right, there's 5 pigeons flying into 4 holes, and we can use the pigeonhole principle. So we've got 2 or more of our numbers landing in one of the holes. And for this particular problem, we can get rid of the or more because all the integers that we were given are different by the question, and each hole can only hold up to 2 of these numbers. So one hole has, in this case, exactly 2 numbers. And that particular hole has a pair that adds up to 9. We don't know which pair, but the pair exists. So we can display the pair existing by one of these numbers as xi and another one of the numbers as xj, adding together to give us 9. And we just say for some ij. You're probably used to a lot of answers in mathematics being some number, your answer is 5, your answer is 20. In the case of the pigeonhole principle, we're trying to show that a scenario exists rather than come up with some number. So the scenario that exists is right here. And that's why we're saying for some ij. We don't know which ij, just it's possible to find an I and a j so that this equation works. Let's try the next problem. All right, so next up, we're going to have a party. And at the party, there's going to be some handshaking going on. And we're supposed to show that at this party, there must be a pair of people who shook the same number of hands. So I don't have very much fun if I party by myself, so we're going to say that the party has to have at least 2 people. Okay, and the question clarifies that it is possible that someone didn't shake hands with anyone. So you're allowed to just sit in the corner at the party and refuse to shake hands if you want to. So what do we want our pigeons to be, and what do we want our holes to be? So the people at the party are each going to be assigned a number. The number of hands they shook. Whatever that assignment is, tells you the pigeons and the holes. The people are being assigned a number, so the people are being assigned to some hole. So our partiers are our pigeons. So not all the partiers are the same, but there's n of them at the party. And each one of these people needs to get a number assigned to them for how many hands they shook. Those will be the holes. So you could be in the corner and refuse to shake any hands. That would be 0. Or you could shake hands with one other person. You could shake hands with 2 other people. On and on and on. You could shake hands with everyone except one other person, or you could shake hands with every single person. I suppose you can't really shake hands with yourself, so we'll have to get rid of that last option. There shouldn't be an n here. So how many does that leave us with in this list? There's n holes. So these n pigeons would fly into these n holes. Now we have a bit of a problem. You'd never want the same number of pigeons as you have holes. That's just going to tell you that it could be that just one pigeon ends up being in each of the holes. But there is a solution to that problem. There's something going on here with the problem where we can have less pigeonholes over here. This number is n. We would like this number to be smaller. Maybe pause the video now and think of a way that that could occur. So if you think carefully, you can't have someone at the party shake 0 hands and then someone else at the party shake everyone else's hand. Those two partiers cannot be at the same party. If we look over here on the left-hand side, let's say this first person says, oh, I want to meet every single person at this party. I'm going to shake n-1 hands, and that's their number assigned to them. But this last person says, nope, I refuse to shake everyone's hand. My number is going to be 0. Those two partiers cannot go to the same party. So we can combine the 0 and the n-1 into the same hole. So that gives us a successful way of setting up the pigeonhole principle where we have n pigeons flying into n-1 holes, and we can make our pigeonhole principle conclusion. So by the pigeonhole principle, we take the number of pigeons, divide by the number of holes, and we round up, and we always get 2 out of that, because this will always be just a little bit more than 1. So 2 or more people shook the same number of hands. And we do have to make sure we include the or more, because these partiers could be social distancers and refuse to shake anyone's hand. Maybe they all decided to pick 0. Maybe they refused to shake hands. Or maybe everyone decided to shake everyone else's hand and they all chose n-1. Or maybe there was a pair of people that shook hands with 2 others, and then everyone else shook a different number. All of those are possibilities, but no matter what, we must have 2 people shaking the same number, and that's what the question asked for. All right, let's take a look at the next one. So in this example, we have a collection of n+1 distinct integers, a bunch of different integers. And we're supposed to show that integers x and y can be combined so that their difference is a multiple of n. We're supposed to show that that scenario exists. So let's try to think about, if it says multiple of n in the question, what might we be able to use as a good tool to deal with that? I'll let you think about that for a moment. So if you thought of modular arithmetic when you thought of multiples of n, that might be a good tool to use here. So our integers that we're given, we have an interest in multiples of n, so how about we use mod to assign to those integers? So we're assigning to the integers values in mod n. So the integers are pigeons, and they're being assigned to their holes in mod n. Let's draw a picture. Okay, so we have n+1 integers that were given in the problem, and they're flying into all the different possible remainders in mod n. So let's apply the pigeonhole principle and see what we get. So by the pigeonhole principle, 2 or more integers have the same remainder when we divide by n. We don't really care about the or more, we just need to think about this pair. So now we can conclude that there's an xi that's congruent to an xj in mod n. And to clarify, this is just for some ij. Don't know which ones, it doesn't matter though. It just exists that there's an I and a j. Okay, now this doesn't quite resolve our problem because our problem was about a difference, x minus y. So how about we consider this number as like the x number and this number as the y number, and we'll take a difference and we'll see what happens. So if we subtract xj to both sides, we'd have xi minus xj is congruent to 0 in mod n. But this means that xi minus xj, a difference, is a multiple of n, because anything that is 0 in mod n is a multiple of n. It's either 1 times n, 2 times n, 3 times n, or it could even be negative n or 0. So we get what we want as our final result now. All right, let's take a look at our next problem. Okay, so here we have a grid. It's an 8 by 8 grid with two opposite corners missing. So that corner's missing and that corner's missing. It says, can you cover the grid with dominoes? Why or why not? A domino takes up exactly 2 squares. So if you want to try this, a domino is something like that. It takes up, those 2 squares. You can just draw a line. I mean, the domino actually looks more like this, but you can just try to fit in, to these spaces and see if that's possible to cover all the spaces. You can't have something like sticking out the side, and you can't have any overlapping. So pause the video now and give that a try. So this type of problem is known as a tiling problem. And when tiling with dominoes on a rectangular grid or square grid, one of the very helpful tools that you can do is checker the grid. So by checker, I mean color in, let's say we have white squares and blue squares. So color in the rest of it checkered back and forth, just like a checkerboard. Okay, so as we complete this problem of checkering the grid, let's count how many white squares we got and how many blue squares we got. Well, if we kept going, this square here would have been blue if that square wasn't missing, and that one would have been blue. And at that point, we'd have an equal number of white squares and blue squares, and that equal number would be 32 and 32. So there are 30 blue squares and 32 white squares. So next, if we notice that whenever you place a domino, because it either goes horizontal or vertical to fit into this space, it takes up exactly 1 white square and 1 blue square. So we have a bunch of dominoes that are being assigned to the space that has a white and a blue. So we can set up the pigeonhole principle if we like. So our grid would require 31 dominoes to cover it, but there was only 30 ways to pair blue and white. There was only 30 blue squares to begin with, the way that we just tiled the screen. So when these dominoes fly into those blue and white pairs, as we have to do when we're tiling with dominoes, the dominoes cannot be uniquely distributed in 31 blue and white pairs. So therefore, there's no way to do this tiling. So our answer to this problem is no. They asked us, can we do the tiling? The answer is no. So what about scenarios where we could possibly do the tiling? Let's investigate those too. Maybe this won't have too much to do with the pigeonhole principle, but I think it's an interesting discussion to have as an extension to this problem. So we now know that if we remove the same color, like if we remove 2 black colors below, we couldn't do the tiling for the same reason as we just looked at. It didn't really matter that the same colors were removed from the corners before. It just mattered that it was the same color. So if this color was removed and that one was removed, they're the same color, you couldn't do the tiling. But what if opposite colors are missing? Could the board still be tiled? So if we just randomly pick, let's just say, this one right here, let's say that one was removed and a white one was removed, could we possibly do the tiling? What we're going to show in this problem is that it's always possible to complete this tiling problem if opposite colors are removed in this 8 by 8 grid. I have 3 steps to show you why that's the case. Let's work on step 1. So in step 1, what we want to do is make a path that loops through the entire grid. So any pathway that works is just fine. There could be lots of them. Let's say I start here and I loop back and forth. I have to go through every square in the whole grid and come back to where I started. So I don't want to go back to where I started just yet. And maybe I'll loop like this, looping through and returning back to where I started. That's one example of how you could do this. Okay, that's step 1. Okay, in step 2, we remove any black square and any white square. Okay, so it didn't have to be the 2 squares that we decided to remove before. It could be any black one and any white one. Let's just stick with the original choices that we removed when we were talking about the problem. So if we remove those, then the pathway is kind of cut off at that point. So from here, we have 2 separate paths. If we go around the loop in the same direction that we made it, notice that this first path goes white, black, white, black, white, black, and then on in that pattern around the loop all the way until we hit the other point where it gets cut off. And then the other part starts going black, white, black, white, black, white, on and on until it gets cut off. So the idea in step 3 is to complete the tiling by following the pathway. And the neat thing is that we can complete the tiling because of that white-black pairing and black-white pairing to tell us that each of these paths is always of even length. Let's write down step 3, and then we'll come back and complete our diagram. So once again, in our final step, we're going to tile the grid by following the path and skip the missing squares that we removed before. And each part of the path is of even length, so we're okay to do that. So if we scroll back up, if we actually want to complete this tiling problem with the original squares that we missed, we're going to place dominoes like so as we follow the path along. So we'll keep doing that and we'll be able to complete the whole picture. Okay, so this explains in more of a complete picture of really all the scenarios that we might be interested in for the 8x8 grid. If any 2 squares of the same color are removed, the tiling problem cannot be solved. But if you remove opposite colors, the beauty is that you can always solve the problem by this solution. I think the solution is quite neat. It's a neat approach to this style of problem. Let's move on to our next problem on the pigeonhole principle. All right, this problem says, given 30 different numbers from 1 to 45, can we guarantee that 2 of them differ by 14? Let's think back to an earlier problem in this video where we had numbers from 1 to 8 and we thought about, can they sum up to 9? This is kind of similar to that problem where we've got numbers and instead of looking at a sum, we're looking at a difference, but it should be a clear comparison to what the pigeons are and what the holes are. So just like before, the numbers are going to be our pigeons and the holes are going to be all the ways that we can differ by 14. Okay, so as we're listing differences of 14, we've got 1 and 15, 2 and 16, 3 and 17, and as we keep moving along, ... eventually we're going to hit the number 14 and 28 to make a difference of 14. Now the next difference of 14 that you might think of would be 15 and 29. But 15 and 29 are not so nice to make as a new pigeonhole because we already have 15 in one assignment in a pigeonhole. So if the number 15 was over here, we wouldn't want it to have a choice of going into one hole or another hole. So what we can do about that problem is, instead of making a new hole for 15, we can use the 15 that's already there and just stick 29 next to it. Okay, now this would create a little bit of an issue if 1 and 29 are both numbers in our list. Like if 1 is over here, 29 is over here, and we stick all of these in the same pigeonhole, then 1 and 29 certainly don't make a difference of 14. So now in this pigeonhole, currently we would need 3 numbers to fly into there to guarantee that we have a difference of 14. In fact, that would give us 2 differences of 14. We only really care about 1. But we can continue on this pattern and just see what happens. We'll see if this works. So we'll put 30 and 31 and so on, completing all the way up to 45. So as we complete writing all of our numbers down, we notice that some of these pigeonholes have been assigned to 4 numbers, and some of the pigeonholes have been assigned to 3 numbers. So the first 3 pigeonholes that we've listed here are assigned to 4 numbers, but then after that there's a little bit of a change. The ones below that are just assigned to 3 numbers. Now it doesn't really matter if that's consistent or not, it's just how many holes do we have. We have ended up with 14 different holes, so let's write that down. There's our 14 holes, and these 30 pigeons will fly into those 14 holes. So let's think about what the pigeonhole principle tells us now. So the pigeonhole principle tells us that 3 or more numbers are in the same hole. So one of these holes over here, there's 14 pigeonholes, and one of them, we don't know which one, has 3 or more numbers. And there's 2 types of pigeonholes that we discussed earlier. Let's think about each type of pigeonhole. Let's say, for example, we have a pigeonhole that has just 3 numbers inside of it. So for example, maybe we have the 14, the 28, and the 42. If that was one of the pigeonholes that had 3 or more numbers, well, I guess it would be exactly 3, there's no or more, and all 3 of those numbers are in that hole. And we arranged things so that any number that was side by side, if they had this side by side connection, they have a difference of 14. And in this case, it happens twice with this difference of 14. We don't really care that it happens twice. As long as it happens once, then we've successfully solved the problem. We successfully found the scenario that we were looking for. So in the case of a pigeonhole that's of size 3, we have success. What about a pigeonhole of size 4? So this pigeonhole of size 4 would have 3 numbers in it, or it could have 4 numbers because it's 3 or more. But we'll just start by thinking about 3 numbers. And no matter how you pick these 3 numbers in this hole, you must pick 2 numbers that have that side-by-side connection. There is no way to avoid that side-by-side connection, even if you consider all of the possibilities. In all of the possibilities, we have at least one side-by-side connection, and the side-by-side connection means that we have a difference of 14. So no matter what, we always get a difference of 14. Let's write down our conclusion in a nice paragraph. So we conclude that 2 of the numbers that we were originally given are indeed side by side in one of the pigeonholes above. So we can conclude that we indeed have a difference of 14. And that concludes our problem, successfully using the pigeonhole principle to find that scenario existing. Okay, we have one more problem for this video. In this problem, we're going to show that by placing 5 points anywhere within a square of side length 2, there will be surely a pair of points that are kind of close together. They're a distance of root 2 or less from each other. Let's start by drawing a picture. So there's our square, and it says that the side length is 2, so we have a 2 by 2 square. And if we think about the distance root 2, that would refer to a square of side length 1, or our unit square. So if we have a 1 by 1 square, then the diagonal is root 2. So what does the 1 by 1 square have to do with the 2 by 2 square? Well, if we think about maybe making a grid on our square so that we have 1 by 1 squares within our 2 by 2 square, then we have 4 sections that the longest distance, which is the diagonal, in each of these 1 by 1 squares, in each of these 4 sections, so that 5 points, when shoved into this 2 by 2 square, by the pigeonhole principle, we would have to have 2 of them end up in the same region. So we just need to set up the pigeonhole principle to try to solve the problem in this way. So our pigeons will be points, and our holes will be these 1 by 1 squares. Okay, so we've got the 5 points, the pigeons, flying into the 1 by 1 squares. And we do end up with 2 points on the one square that might have 2 or more points, but there is a little bit of a problem. If our pigeon, let's say, lands right on the line, let's say our point lands right here, which pigeonhole is it a part of? Is it a part of this pigeonhole, or is it a part of this pigeonhole? So maybe we should make that clear. One notation that you can use to kind of help this along is you could use dotted lines versus full solid lines. So let's say we erase this line right here, that side of the square, and we'll say that that line will be a dotted line. So the region in the top left will include everything going all the way up to that dotted line, but not the dotted line itself. So we'll have to make a choice with each one of these dotted lines, which way it's going to go. So maybe we'll be fair and we'll give one dotted line to each of these regions. So as we go through, we'll complete that. Now there's one last part of our 4 1 by 1 squares that we haven't distinguished, the very middle. So one way to notate that is like with an open circle. If we notate an open circle, it means we can go all the way up to the middle, but we don't include the middle. Now one of these squares has to get the middle, so how about we pick the top left? So now we can successfully use the pigeonhole principle to get a conclusion. So by the pigeonhole principle, we have the number of pigeons divided by the number of holes, and rounding that number up to 2. So we have 2 or more of our points are in the same 1 by 1 square. And these 2 points that are guaranteed to be in the same 1 by 1 square are a distance of root 2 or less apart. And this successfully concludes the goal that we tried to set out in this problem. So I hope you enjoyed all these examples about the pigeonhole principle. Thanks so much for listening, and we'll see you on the next one.